And this is where we're going to get started. If at any time you develop any questions or you have something you need to say, please just put it in the chat window. We will try to address it as they come. But we need to talk about the neuron and the nervous system, both the structure and the function thereof. So the neuron itself, we'll learn about food cravings when we start talking about like your senses, which is, I believe, the next unit. Yeah. All right. So the neuron is the basic building block of the brain and the nervous system. So basically every single muscle fiber, gland, sense is connected to the brain through these system of neurons. And your basic neuron contains something that looks very similar to the picture that we've got here. It has the cell body, which is right here. Extending out from the cell body are dendrites. Okay, so they're the fingers reaching out to communicate with other cells. Then one strand of that nerve fiber goes down what they call the axon, which is that one strand, which goes to the axon end terminal or end bulb or axon terminal. Inside the end bulb contain chemicals that we call neurotransmitters. And these neurotransmitters are what communicate between neurons. So from neuron to neuron, they are using these little tiny chemical messages to go back and forth between them. It is a one-way process. When the neuron fires, if enough neurotransmitters input onto the dendrites, they excite the cell body, and that fires an electrical charge down the axon to the end bulb, which then launches off all of the neurotransmitters to the next waiting dendrites, to the next cell. Okay, so the axon is covered in this fatty material called myelin. Now, myelin is kind of grayish in color, and it's basically just fat. And that fat acts as an insulator because our entire body is wired for electricity in absolutely minute amounts, but we are wired for electricity. So if two axons were to touch one another, you could get a short circuit and you could get neurons going in all different directions, which some people argue causes different disorders, different neurological disorders that they can't control. Okay, but the myelin actually works to insulate the axon so that they don't short circuit. There are people who have they have a smaller amount of myelin than most people, and those people do have neurological disorders. What those are off the top of my head, I don't know. But those people do exist, and it is very difficult sometimes to be them because their myelin is not insulating their axon enough, and so they tend to lose control of bits and pieces of their body. Okay, so the dendrites receive the information and send that to the cell body. The cell body then sends an electrical charge down the axon, okay, to the end bulbs, which then release neurotransmitters that go to the receptor sites on neighboring dendrites, continuing the process. So if you touch your finger with your other finger or with anything else, okay, your skin sensors are receiving information, turning it into an electrical impulse, which then travels down your finger into your hand, through your wrist, down your arm, through your elbow, up your arm, to your shoulder, where it makes a right-hand turn and goes up into your brain. Your brain then processes that information to figure out what it feels, and then it goes, I feel pressure. That's what that is. All of that is taking place basically at the speed of light, okay? But it is kind of a long way for those electrical impulses to get transferred from one neuron to the next, 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 all the way to your brain, where a bunch of neurons fire and go, I feel pressure, or I feel hot, or I feel cold, or whatever you happen to be feeling. Okay. Same thing with your eyes. Your eyes are absorbing light radiation, translating that into an electrical impulse. That impulse is being sent up to your brain. It's being processed, and it gives you the sensation of sight. Okay. But the neuron is the building block of all of that. And your brain is made up of billions, if not trillions of neurons, all interconnected within one another. Okay. So the neuron and understanding how it works makes it so that we understand how the brain functions, how our senses function, and how they can go wrong, because they can go wrong due to genetic disorders and things like that. Okay. Now, neurotransmitters. This is a list of some neurotransmitters. Not all of them are listed, so don't worry about that. And you don't have to know exactly what each of these things do, but you do need to have heard of these. So we're going to go quickly through them. So the first one is acetylcholine. This one helps with muscle contraction. So when your neurons release acetylcholine, it will regulate whether or not you are gripping something hard or gripping something loose, because it causes the contraction of your skeletal muscles and allows you to move. Okay. It also helps to regulate your heart rate, promotes arousal in the brain, and transmit messages between the brain and the spinal cord. If you have low levels of acetylcholine, that means your arousal and your attention is low. Okay. There are studies that are showing that low levels of acetylcholine can actually be associated with things like Alzheimer's disease. Okay, your attention just kind of starts to be a little low, and you're just not very, I don't want to say aroused, because that tends to have a sexual connotation, but you just don't seem to be, nothing seems to get you out of bed. You just kind of like, I'm fine, I don't need to do anything. And you just kind of are slower. Okay. Then there's glutamate. Okay. Glutamate stimulates receptors associated with learning and memory, as well as many sensory and motor functions. Glutamate is the most abundant excitatory neuron or neurotransmitter in the brain. And overabundance of glutamate may lead to migraine headaches. And it's also oftentimes associated with a chemical that is often added to food because it makes food taste so much better, and that is monosodium glutamate. Because we are getting too much MSG, it might actually, kind of flood our brain and give us migraines. Some people called it Chinese food syndrome, where people would go to a Chinese restaurant and then later that night they would get these really bad headaches. That's actually not a thing. You don't get a headache from eating Chinese food. That's just actually racist. So it's not a thing. But there are people who can be a little bit overly sensitive to MSG, and MSG is in lots of different things. Back in the 1970s and the early 1980s, it was actually really popular. It was kind of like the gluten of its time. Everything would say no MSG, contains no MSG. It actually did contain MSG. It just had naturally occurring things. But MSG is in a lot of stuff, and it makes food taste a lot better. But it's nothing to be afraid of. Okay. We have GABA, or gamma aminobutyric acid, which inhibits the firing of neurons, and is the most abundant inhibitory neurotransmitter in the brain. So there are neurotransmitters that are trying to make your neurons fire, and there are neurotransmitters that are trying to get your neurons to stop firing. Okay, glutamate makes them fire. GABA makes them stop. It inhibits the excitatory ness of the neurotransmitters, or of the neuron. It is associated with calming effects. A lack of GABA is connected to seizures, tremors, insomnia, anxiety, epilepsy, and Huntington's disease. So there's lots of different things that can be associated with a lack of the neurotransmitter. Dopamine, which is probably something that you've heard of. Dopamine is primarily involved in processing smooth and coordinated gross motor movements and in attention, learning, and reinforcing effects of several often abused drugs. So when you get a shot of dopamine, your brain kind of gets that little, that feels good. Okay. You feel coordinated. Everything seems to be going really well. Okay. Having coordinated movements instead of short, jerky movements, okay, is associated with dopamine. When we watch the movie on Thursday, or when you watch the movie on Thursday, they're going to be talking about dopamine as an additive to be added to the patients that they're going to be talking about, and that's going to help them to get better. Okay. So dopamine release in the nucleus is linked to addictive drugs, addictive sex, attention-grabbing experiences. Okay. Your phone is designed to actually give you a little hit of dopamine every single time. Okay. Especially like games. Facebook also gives people a hit of dopamine when somebody agrees with them or likes their picture. That's why people want those things. I got to get all these likes. Who the hell cares? Well, I have to get likes. No, you don't. That does not matter in the greater scheme of things. And yet there are a lot of people out there who obsess about that. It's because of that dopamine hit that they get from it. They feel good about themselves. Even when they're doing really horrible things, they get that dopamine hit, they feel good, and that keeps them coming back, which is why people call it a phone addiction or a video game addiction. It's because it keeps you coming back for more of that dopamine. If you beat that level again, ooh, it feels good. Okay. When you get a prize, ooh, it feels good. And they know, and they've done, especially game design, has done a lot of psychological research to keep you coming back without having to give you too much. Okay. If you've ever played a game and you're just not good at it, you probably give up after a while. You're like, screw this. I'm not playing this anymore. I hate this stupid game. That's because it's not getting you that dopamine hit. If the game designers had done things just a little bit differently, they could kind of just give you a little nudge of dopamine, make you feel good, keep you coming back for more. The first hit is always free. Then you've got to pay. Sorry. Just went back to my previous job. Anyway, I really wish I knew if that landed. Anyway, norepinephrine is another neurotransmitter. This is found in our autonomic nervous system, and we'll talk about that in just a second. Norepinephrine governs sympathetic arousal by activating our heart and blood vessels, thus giving rise to the fight or flight effect, as well as other excitatory actions. It's released in the brain to enhance attention and memory for emotionally charged events. So when something really, really emotional is happening to you, your brain is kind of flooding with norepinephrine so that you remember this. This is a big, important thing. Serotonin plays a role in the regulation of our mood, control of our eating, sleep, arousal, the regulation of pain, and control of dreaming. So this one is kind of what helps put you to sleep at night and then wake you up in the morning. Okay, so when the sun goes down and your brain stops, or your eyes stop seeing the sunlight, your brain starts pumping you full of serotonin. And as it starts getting more and more serotonin, you start getting sleepier and sleepier until you're out like a light. Then when the sun comes up, you're through your eyelids, you get a little bit of sunlight, and that starts stopping the production of serotonin, and that starts to wake you up and get you going. Okay. Most of the what are those drugs called? got such a headache. Too much MSG. Oh God, I've got it like on the tip of my tongue and it won't come out. Things with the guy. Antidepressants. Most antidepressants try to affect serotonin, as that can lead to depression if you're not getting enough serotonin. So you want to get a little bit more of it. So that's what most antidepressants are doing. And then you have endorphins. Endorphins are kind of the brain's painkillers. So when you are hurt or you're injured, like for example, my elbow is still killing me, my brain is releasing a little bit of endorphins for me to get through the pain of it so that I can continue to, get things done wherever possible. Okay. You might have heard of people, who are runners and they get that runner's high. Yeah, that's the endorphins in their brain convincing them to, no, you don't feel this pain. Yeah, no, keep running. Yeah, just keep going. Yeah, not a chance. Not a chance in hell. I have a car. That's what they're there for. So anyway, endorphins kind of help to keep you going even when you probably should stop again, like when you're running. Okay, so those are some of the basic neurotransmitters. The way that a neuron functions is it is in a natural state at rest, meaning nothing is happening inside of there. There is the potential for action, but nothing is happening. The neuron is at rest. Now, when the neuron starts receiving information from its neighboring neurons, it receives that stimulation through its dendrites. Now, the dendrites reach out to the end bulbs of the other neurons around it. And the more connections that you can make between neurons, the faster your brain can operate. If you've ever watched somebody do a speed run of a video game, that person has, their neuron connections are so strong in that particular game that they can probably play it blindfolded and do better than you. Okay. But it takes a lot of practice and it takes a lot of stimulating that connection until there's a really, really strong connection with lots of dendrites reaching out to lots of end bulbs. And it just goes super fast then, because as it receives the neurotransmitters from the neighboring neuron, it stimulates the neuron that we're looking at into action. And when I say by into action, it's the cell body depolarizes. It goes from a negative charge to a positive charge and sends electricity down the axon. And as it sends it down the axon, it reaches the end bulbs, which release all of their neurotransmitters, and the process starts on to the next neuron and the next and the next and the next. While that's happening, your brain has to recover from the process. So as it is, once it has fired, it needs to recharge. So it has to regain that electrical potential. So it has to recover in that state. Okay. So you go from rest to being stimulated to firing to recovery, and then back to stimulation, fire, recovery, stimulation, fire, recovery. And your brain is constantly doing that all day, every day. From the minute you're born until the day you die, your brain will be processing that information by firing these neurons, these simple cells that are deep inside our bodies. Okay. All right. Transmission from one neuron to another happens across a very, very, very small gap between the two neurons. So this is a zoomed in picture of the end bulb of one neuron and the dendrite of another. So you see here, we've got these little tiny things filled with neurotransmitters. We call those the vesicles. You don't have to know that. So the vesicles are filled with chemicals, and they are excited by the electrical impulse, and they release the neurotransmitters across the synapse. The synapse is that gap between the two neurons, which is like a micron in width. It is very, very small. There is not a lot of space between neurons. They are packed in there together. Okay, so the synapse releases the neurotransmitters, and they are absorbed by the neuron of the other dendrite. And it works like a lock and a key, because there's different types of neurotransmitters that can excite or inhibit the excitation of neurons, depending on what kind of chemical they fit into. So one chemical will fit into one lock, and another will fit into another. Okay, so there's two different locks. It's not just a sponge absorbing everything. And once that process is completed, whatever is still in the synapse gets sucked back up by the other neuron. Okay, so the sending neuron sucks back up whatever it takes, and that's called reuptake. That's one of the things, for example, the medication Prozac. It is a selective serotonin reuptake inhibitor, which means, or an SSRI, which means when your sending neuron releases serotonin into the synapse to be absorbed by the other dendrite, normally what would happen is it would reuptake that serotonin. What Prozac does is it keeps the serotonin in the synapse until it gets absorbed by the receiving neuron. So therefore, it doesn't just go away. It will get sucked up and into there and excite it to the point where it will go, so that you don't have a lack of serotonin. Okay, so that's how one example of a antidepressant works. Okay, so the synapse is that little tiny gap between neurons. They release the chemicals across the synapse into the receiving. Okay, the lock goes in, or the key goes into the lock. It excites the neuron or it turns the neuron off, either one. And then whatever doesn't get sucked up or doesn't get used gets sucked back up to be used again. So it's a constant pitching and catching. And then it just kind of, then whatever's left gets taken back. Taken, pitch, catch, taken back. Pitch, catch, taken back. Pitch, catch, taken back. And it's constantly happening all of the time throughout your brain and your nervous system. Speaking of nervous system, your nervous system is very, very simply organized. There are two parts to your central nervous system, the central nervous system and your peripheral nervous system. Your central nervous system is made up of two parts, which is your brain and your spinal cord. Okay, those are the two parts of your central nervous system. Your peripheral nervous system is everything outside of your brain and your spinal cord. So all of the nerve endings in your arm, in your legs, in your torso that isn't your spinal cord, everything else that isn't brain or spinal cord is peripheral. Your peripheral nervous system is made up of two parts, the somatic nervous system and the autonomic nervous system. The somatic nervous system takes care of all your voluntary functions. So the fact that you can wave your arm back and forth, that is your somatic nervous system doing that. Your autonomic nervous system is what controls all of your non-voluntary function, your heart rate, your breathing, things that you can't control, things like when your skin contracts, when you're cold and you get goosebumps. You can't control that. You can't give yourself goosebumps. It's like, oh, it's not doing it. You can't. You have to have it very, very cold. And then suddenly, oh, there's the goosebumps. Aha. That's part of your autonomic nervous system. Digestion. Okay, you don't have control over your digestion. Your body just does it without thinking. Okay, that's part of your autonomic nervous system. Your autonomic nervous system is split up into two parts, the sympathetic system and the parasympathetic system. Now, when we talk about the non-voluntary parts of your nervous system or your body, we're talking about things that you don't have to think about in order to do. You don't have to think, breathe in, breathe out, breathe in, and breathe out. You don't have to think, heart, keep beating. You don't have to think about that. It's all taken care of. It's automatic, but it's not automatic. It's autonomic. I don't know where they got the name. It doesn't matter. Fact is, when your body is suddenly needing to run away, It's got to make sure that it is prepared to being able to do that. So that's where your sympathetic nervous system comes in. The sympathetic system keys you up and gets you ready to go. It's your fight or flight response. So for example, let's say you're in your room right now. Let's say the door slowly opens and in walks a bear. Okay. Your autonomic nervous system is going to kick into high gear and get you ready to either fight the bear, which I don't recommend, or run from the bear, which I highly recommend. There should be a U-shaped hole in the wall behind you. Okay. The parasympathetic nervous system increases your heart rate, increases your breathing rate, dilates your pupils, makes you pay attention to more of the stuff that's going on around you, stops your digestion. Okay. As a matter of fact, it can have the tendency of also restricting your digestion so much that it's like, okay, everybody out of the pool. Okay. So if you've ever been around somebody who is so scared that they threw up, that's their sympathetic nervous system getting them running or getting them ready to run like hell. Okay. So the sympathetic nervous system keys you up and gets you ready to go. The parasympathetic nervous system brings you back down to a normal state. Now, once you've run away from the bear and you're safe, the parasympathetic nervous system can kind of kick in and go, wow, that really sucked. Oh, who's hungry? And get you right back to where you were. Okay. So that is kind of the basics of the nervous system. Okay. Everything is about keeping you alive and keeping you going in the correct direction. And that's basically what it does. Okay. We will talk at length about the brain next week. But for right now, we're just talking nervous system. So we've got the nerves, we've got the nervous system. And let me see if there's any questions that I may have missed. Yeah, but you can't outfight a bear, and you have a far better chance of outrunning a bear than outfighting it. So be honest with yourself. If you get into a fist fight with a bear, you ain't gonna win. Okay.